and a very good day. Salam sejahtera. Okay, we meet again here in this channel. I'm Shikin Aziz. For today's lecture, let me introduce first. Basically, this material is for distance learning for my student who's taking EPF 4801 Process Equipment Design. And for today's content, I'm going to describe to my student on topic of Hopper design step by using TUNRA analytical expressions. So TUNRA is actually short form for the University of Newcastle Research Associates at Australia. All right. So, okay, let's proceed. Oh, by the way, for reference for this lecture content, you can refer inside the description box below. All right. Okay, as has been explained in previous lecture, so this is common design questions, okay, that need to be answered for designing storage for bulk solids, such as particle or any grain, all right, powder, okay. So, for today contents, okay, the main reference is taken from this article from Powder and Bulk Engineering, right? This article written by Greg Mehos, all right? Okay, so for today's for this lecture content, mainly it cover the calculation for outlet discharge diameter, the outlet size or discharge diameter. Other term for it is discharge diameter, and then second is Hopper angle for mass flow, and third one is discharge rates. Okay, now let's proceed for calculation for minimum outlet size. Minimum outlet size or discharge diameter for mass flow. Okay, as been described in previous lecture, for the calculation of the bulk solids design, bulk solid storage design, I will only focus on mass flow because mass flow has many benefits for food industry applications. All right. If let's say you would like to consider final flow for your future application later on, all right, you may refer the article that I referred, and then the reference, the list of, and the you can refer from the list of references that I provide. Okay, for calculation for outlet size, okay, it's actually somewhere around here. We would like to determine how much we need for this diameter of this outlet. Okay, first things, some of the parameters we need to have it, we need to collect it, and we need to analyze it from the lab test. Okay, lab test that we perform on the powder, on the bulk solids that we are handling. Okay, such as cohesive strength, internal friction, compressibility. Okay, this is symbol for angle of wall frictions, permeability, major principal stress. Okay, this one is effective angle of frictions, kinematic angle of internal friction, bulk density, and cross-sectional bed area. Okay, now for steps 2, we need to estimate the Hopper flow factors. Okay, the Hopper flow factors. So you should know that okay, the flow factors, okay, the flow factors is actually a function of the powder's effective angle, all right, internal friction, and the Hopper angle, the powder effective angle of internal friction, Hopper angle, and the wall friction angles. And then Janaike has defined this flow factor by using and actually a typical flow factors is range between 1.2 to 1. All right, so we need to estimate within this value. Okay, within this value. Then the third steps, we need to plot the flow factor and flow function. Okay, so basically if using graphical method, of course that you need to plot lah. Okay, you need to plot the flow factor and flow function, but by applying the analytical expression, most of the solution involve with application of mathematical equation, okay, which has been derived, I think which has been derived from the graphical method. All right. Actually, there are a lot of analytical, okay, there are a lot of analytical expression you can refer from literature. But here I only focus on TUNRA analytical expressions. All right. So as we refer, this is just to refresh your understanding from the previous lecture. All right. So this graph shows okay, this graph shows flow function here, flow function plot, and flow factor. This actually is 1 over flow factors. Okay? Slope of 1 over flow factors. Okay, this is a method if you graphical, okay, graphical method or Janaike method. So where the superimpose of flow factor line, flow factors, and the function, all right, where there is an intercept around here, okay, around here, okay, then from there we can get the solid stress, okay, the solid stress. So right, so there are three possibilities. Of scenario that you will get after you superimpose the flow factors and the flow function line. All right, either the two curve, okay, where the two curve, it can be the two curve do not intersect. Okay, do not intersect. Okay, where the flow function lies below the FF. Where flow function lies below the FF. Alright, the flow function lies below the FF. So the flow function lies below the flow factor, is somewhere around here. So this is the condition, okay, around the where this intersect, so the flow function lies below the flow factor. Okay, so basically what does it mean by this area is there is no minimum outlet dimension requirement to prevent cohesive arching, where if the flow function lies above the flow factor and the curve do not intersect, okay, where flow function lies above, okay, flow function lies above, okay, this area, okay, in this area. Alright, so basically the bulk solid will not flow due to gravity alone, and another means of discharge power is employed. Alright, so you may add another equipment to assist the flow from the silo, okay, such as vibrator. That is some other things that I can think right now. Okay, let's proceed for the third one. Alright, where the flow function of FF intersect as shown in figure. Okay, like this one, there is an intersect, alright, intersect here. So that means that the arch stress and the cohesive strength of the bulk solid are the same and equal to the critical stress. But remember class, when we first try with flow factor, we estimate the flow factors. What we get is actually not a critical, okay, it's not a critical stress, but it's actually I think a solid stress, the other name of it. Alright, because we need to do a repetition of calculation in order to get FF until it converge. Then we can get, when the flow factors converge, then we will get a critical stress at the intercept. Okay, so here is the critical stress. But you will get this after flow factors is converged. Alright, how to get that with analytical, okay, analytical expression. So, this is the things, okay. Before the flow factors converge, the stress that we obtaining from the flow, from the intersects of flow functions and flow factor it's namely solid stress at the outlet. Okay, alright, it's named a solid stress at the outlet. Alright, so this is the step. This is required in order to converge. Okay, first of all, alright, you need to get the regression of flow function test data. Okay, where this is an equation, right? From this equation is obtaining from the data of the flow properties testing data. Okay, in is a lab data. Alright, and then from this data, from the regression line data, and then you need to set the equation FC equal to this symbol sigma, this one. Right, and then we need to solve the solid stress at outlet from regression equation of FC, okay, and with this equation by using decimal notation. And then step 4, you need to substitute. Sorry for that. My eldest, okay, my eldest son. Alright, busy body. Okay, so sorry for that just now, my eldest son. That's my eldest son. Come. Okay, this is my eldest son, Hide. Alright, busy body boy. Go. Pergi Fasife. Alright. Okay, sorry class. Okay. Alright, then where are we? Okay, we need to substitute this solid stress into regression equation of effective angle of friction data. Okay, this again from the lab analysis, and then we need to calculate. Okay, to calculate this symbol. Forgot the symbol name. The delta symbol is for, where are you? Effective angle of friction. Yalah, effective angle of friction. Sorry for that. Alright. And then 5, we need to update flow factors by using Arnold and McLean equation, Johansson equation. I will show you after this. And then number 6, we need to update this in step 2 and 3. With step 2 and 3, we repeat, and then we will get a new solid stress. New solid stress here. We will get to repeat this method. Okay, in sigma 1 into this equation of data to the angle of friction fraction, and then after that we update this effective angle of friction. Next thing, after we update flow at 5, okay, by using the equation. Alright, where is the equation? Let me show you now. Okay, this is the equation. So there are two types of equation in order to calculate factors. Alright, in order to calculate flow factors. Compared to previous lecture, we can obtain flow factors by referring to a design chart. Alright, design chart. But now we are applying an analytical expression. This is TUNRA analytical expression. So there are two types. One is derived by Arnold and McLean, where here is for powder. Here is for powder with low water. You can use this equation, and this I to denotes a shape of outlet, either circular or then next another equation, second equation for flow factors, Johansson, okay, for wall friction above 12 degree and Halbe angle friction near the mass flow boundary. Alright, so you should know that B2 and 1.7. Right? Okay. So we will repeat this. You need to repeat this step until FF is converged. Flow factors is converged. So how to know flow factors is converged? The previous flow factor and the new one that you get, you minus the current flow minus the previous flow factors. If you get close to 0, that means it's converged. Okay. After we update flow factors, the solid stress, and the effective angle of friction, then we move to step 5, okay, where we are going to calculate the critical cohesive strengths, okay. Alright. Previously, we calculate critical cohesive strength by using a graphical method, where from the intersect here we will get a critical cohesive strength. But here we are going to use this equation, this expression, these analytical expressions. So you can calculate critical cohesive strength by using this. So basically what I mean by the critical stress? Okay, so it's actually determined from the intersection of the flow function and the converged flow factors. Okay, as you know, and at the point where they intersect here, it means that the arch stress and the cohesive strengths of the bulk solid are the same and equal to the critical stress. Alright. So which means that the flow, there is no arching. There is no arching. Okay. Okay, then step 6, we have to calculate minimum outlet. Okay, how are we going to calculate it? By using this analytical expression. Okay, where here for design purpose, we can assume this function of h delta equal to 2.3, And then the bulk density here is the bulk density under a consolidation corresponding to sigma critical with these functions of critical, this FC critical flow function critical. And this can be where how to get this is from regression of the bulk density data from the lab analysis. All right. Okay, so we have done calculation for minimum outlet diameter. Now, I'm going to show you how to calculate the Hopper angle. Okay, the Hopper angle using TUNRA analytical expression. Alright, the first step is we need to specify the outlet diameter greater than or equal to B mean. Okay, we need to specify. So we already knew the outlet diameter. Okay, from the data that we obtained from the previous step, the previous slide, the calculation of minimum outlet diameter. Alright, from there we can specify the outlet diameter in this step, okay, in order to get a Hopper angle. Alright, so commonly the best to specify is by choosing greater than equal. I prefer, okay, find a greater than the B mean that you obtained in previous slide. Alright, and then we need to calculate the solid stress. Okay, for this step, the calculation for solid stress, okay, is by using this analytical expression. Okay, by using this analytical expression, where again here, this function has, we can set it as equal to 2.3. Then next, we need to update the effective angle of friction and the wall friction. Alright. So how to update the effective angle of friction? Okay, by substitute the stress, the sigma 1 that we obtained in previous slide, into the effective angle of friction data. Okay, it's basically a regression from the regression equation of the analysis data. And then we can calculate a new effective angle of friction. And then after that, we calculate the wall friction by using this analytical expression. Okay. Wall friction, okay, by using this analytical expression. Alright. After that, okay, by the way, the things, okay, that's a bit complicated here. Alright. Okay. The equation looks straightforward. Okay, looks straightforward, simple. Alright. But we need to identify this value and this value here. Okay. So, okay. This value is, this symbol is for shear stress at the wall. Alright. So why we need to identify this? Okay. According to the literature, the wall friction angle depends on the effective angle of friction, delta here, and the solid stress normal to the wall. Okay, normal to the wall. This is solid stress normal to the wall. Okay. From the regression of the flow properties testing data, so wall yield locus can be described by this, okay, by this equation. So we by solving this equation, we can obtain the solid stress normal to the wall, and we can as well obtain the shear stress at the wall. So how to solve this equation is we need to apply a list of equation here. Alright, where here a solid stress normal to the wall can be calculated using this. Alright, using this, where beta and where the constant here need to be calculated by using the equation below here. Alright, so there are several steps of calculation. Okay, and then finally you will get this value, these two value. Then later on you can solve this. Alright. Okay, then step 4 is to estimate the recommended mass flow Hopper angle. Alright. Mass flow Hopper angle by using this equation. Alright, by using this equation. Okay. So basically the Hopper angle required to allow mass flow depends on the effective angle of friction. Okay, depend on effective angle of friction. Alright, this one. Okay. Delta and the wall friction angle. The wall friction angle. Okay, this one, wall friction angle. Okay, beta is depending on wall friction angle. And the Hopper's geometry. Alright. Okay. So, this equation is for conical. Okay. This is for mass flow conical. Right. Where after you obtain the Hopper angle, you need to subtract the value by 2 to 3 degree. Okay, from the above equation. And then another equation is for slotted. Okay, for slotted outlet. Okay, this is for slotted outlet. This equation. And this is for wall friction less than, hold on, this is for wall friction. For wall friction less than delta minus 3 degree. Okay. Delta stands for effective angle of friction. Okay, effective angle of friction. And then the outlet length for this design must be at least 3 times its width, alright, or 2 times its width if the transition hopper end walls are vertical. Alright, for this equation, there is no safety factors applies. Alright, in fact, hopper slope 5 to 10 degree greater than what be suggested by this equation, you may still get a mass flow. Okay, mass flow discharge pattern. And then after that, step 5, we need to update the function H here. This function H, okay, is parameter the H parameter is used in the to calculate the critical outlet diameter to prevent arching. Okay, and then we need to update this by using the estimated value of hopper angles, alright, that we obtained just now. Okay. And again, this value I is to differentiate between the design for circular outlet shape, circular outlet geometry, and slotted outlet geometry. Alright. After updating the function H just now we need to update flow factors, the solid stress, the angle of friction here, wall friction, angle of wall friction, and then here is hopper angle. Okay, we need to update all these parameters. All right, so how to update the flow factors? We were using the Arnold and McLean equation or Johansson equation as shown before this. All right, and then for solid stress, we will update using this equation. All right, and then for updating the effective angle of friction, we need to substitute the solid stress that we obtained from step 2 here into regression equation of effective angle of friction data from the lab testing data. And next thing, we need to update the wall friction by solving this equation. As I shown before, this series of equation need to be solved in order for you to obtain the what they call here, wall yield locus, and another one here is the uh, solid stress normal to the wall. Then after that, we need to update again the hopper angles by using the equation that we have. All right, and then we need to repeat this step. All the above step here we need to repeat until we get solid stress. Okay. So once we get a converge solid stress here, that's mean the hopper that's mean the latest hopper angle that we obtain is the recommended hopper angles. Yeah. All right. Okay, now let's look calculation for discharge rate. Okay, calculation for discharge rate. All right. So the maximum steady solids discharge rate can be permeability and compressibility testing data. All right. From this equation, it shows the maximum steady rate, and this equation can also be represented by using the velocity of the solid's velocity. Okay, the bottom equation here. Okay, the solid velocity. And then this dp over dz is gas here. O here is velocity equation. Okay, can be solved. Okay, by substitute this expression, the pressure gradients expression, and then we will obtain this. So basically, in order for us to again, we need solid after obtaining we can calculate rates. All right. Okay, that's it. Okay, the TUNRA. Okay, the TUNRA analytical expression. Okay, a method to solve. To solve. Not to. The method to. The method to calculate. Hopper angles. To calculate the minimum outlet diameter and discharge rate. All right. So it involves a series of steps, all right, and we will do a tutorial, okay, later, via online class, okay. So either I'm going to use a Google meeting, or we can use Zoom, okay, and then I will announce for this later, okay, the date for this, all right. So see you again in the next class, and I hope this material can assist your design work, okay, for your project design. All right, class. Bye. Assalamualaikum.